Swayam Prabha. Digital India. Educated India.
So let me explain again the rationale for discussing porous ceramics in general and how that ties to the topic of the course on additive manufacturing of ceramics. As I mentioned, most of the applications for components that have been manufactured by using additive manufacturing contain porosity. And the advantage, of course, of additive manufacturing is that you can control precisely the position of the pores, the size of the pores, the shape of the pores, the amount of the pores. And with the techniques that I have described for producing porous ceramics, that's not the case. You cannot typically easily select or define a certain pore size and pore size distribution. But the message is that, well, further we will talk about the properties of porous ceramics. So this ties into, this applies also to components produced by additive manufacturing. But one of the things that I said during this course is that you do not necessarily need to use additive manufacturing for making everything that can be used from the point of view of ceramic components. So it makes sense to realize that you can produce, for instance, highly porous ceramics using also other fabrication methodologies. And then, of course, you need to decide if the cost, the properties, and the combination of these factors lead you to producing these components using additive manufacturing or using, for instance, different foaming technologies. So we are almost finished concerning the part on the fabrication. We mentioned that different methods have different strengths and lead to components with different characteristics. I would like to mention one final way of producing ceramics, porous ceramics, still using direct foaming. And one of the reasons for presenting this approach is that this is quite a unique way of generating foams with specific properties. So we mentioned that foaming of a liquid is quite simple to do. You can simply froth the liquid. Of course, the liquid is a suspension containing ceramic particles. You can inject gas. You can have something that decomposes and generates gas. So, and apart from generating the liquid, then once we have the liquid foam, we need to decide how we're going to set the foam. In between these two stages, foaming and setting, and therefore obtaining a solid component that allows it to be further processed by sintering, we have the stabilization of the foam. And I mentioned that you can use surfactants in order to do that. And this is quite an effective way of achieving what you need. However, there is another approach called Pickering foams. And Pickering was a British professor in the 1910s, I think. And he realized that you can stabilize a foam, therefore you can stabilize a liquid and a gas bubble, not by placing surfactant molecules at the interface between the liquid and the gas, but by placing particles between at the interface. And these particle stabilized foams have very interesting characteristics because they are extremely stable. So this means that all the processes that lead to the collapse of the foam are very inhibited. And this leads to the possibility, for instance, of avoiding coarsening of the pores, which is the coalescence of bubbles, and with the disappearing of the small bubbles and the increasing size of the large bubbles. And you can see here, for instance, with the regular foam with surfactants, after 4 hours, this is the initial foam. You can see the small bubble size. And after 4 hours, you have fast coarsening and then the destabilization, drainage, and film rupture with the collapse of the foam. The Gillette razor foam is quite stable, and you can see that the increase in bubble size occurs quite slowly. But if you do the particle stabilized foam, you can see that you do not have coarsening for a very large a very long amount of time. And there were two research groups working in this field. The main one was the one led by Professor Gaukler in ETH Switzerland, which in the early 2000s developed this approach specifically for ceramic foams. And bear in mind that Pickering was simply adding some particles to his liquid, and because the particles were functionalized, they could sit specifically at the interface between the liquid and the gas. So the vast majority of the volume was occupied actually by liquid. With this approach that was proposed by Professor Gaukler, you have a slurry, but you functionalize a slurry made of containing ceramic particles, but you functionalize some of the particles so that they preferentially sit at the interface between the liquid and gas, leading to the stabilization of the bubbles. And they studied how you can achieve that, and it's a matter of surface tension. And in order to have the possibility of obtaining foams properly, you need to have an intermediate wettability between the liquid and the solid, and you can functionalize the ceramic particles using specific chemicals. For instance, they used short chain amphiphilic molecules as surface modifiers. And actually, there are two approaches to this. Some people, like Gaukler, actually functionalized all the particles, and simply some of them were reaching the interface between water and air. Other people functionalized only a specific amount of powders within the slurry and added that to obtain a particle stabilized foam. And you can see here, after frothing, you obtain a foam which is very, very stable, very rigid. Of course, you can control the amount of water in order to have it make it flowable. And after that, you simply need to extract the water from the system, and they did it by freeze drying. And then you have your solid foam that needs to be sintered. One interesting feature of this approach is that you can apply it to not just to ceramics, but also to metals and plastics, assuming that it makes sense to apply it to plastics, because typically you can foam them quite easily, maybe not polytetrafluoroethylene though. So there are several parameters that you can use to modify the macrostructure as usual. Of course, the concentration of the suspension, the shear rate and method of expansion, the amount and type of amphiphial, And with this approach, you can obtain very, very, very large volumes of porosity, higher than 90 volume percent, and you can obtain very small cells. One characteristic of this approach is that the particles, functionalized particles, sit preferentially at the interface between the liquid and the gas. And this leads to closed cell foams. And a lot of applications for ceramic foams or porous ceramics require interconnected porosity. So this is a little drawback of the approach. It simply means that this is a very good approach for making specific components, for instance, for thermal protection. A little bit less favorable for making open cell components. In order to generate open cell components, you need to perform the process in a way that is not optimized. So you need to make sure that not all the surface of the bubbles are coated with particles, because if that's the case, then you get you get a closed cell. One interesting feature of this approach is that you get very, very high strength. And this is due to the fact that the cell walls are very thin. You can see here, basically, they are constituted by a single layer of particles. You can see that I mentioned that it is difficult to obtain open cell foams, but you can also achieve that. Of course, being this a direct foaming approach, you typically have cell walls with cell windows. So the permeability is not as high as you would have for a reticulated ceramic. One additional interesting feature of this approach is that once you have your foam that is constituted by bubbles that are stabilized, gas bubbles that are stabilized by particles, what you can do is that you can dilute the system and the particles remain stable. And then this allows you to make hollow capsules. So and the control in size is quite nice. So this is a very nice way of producing ceramic capsules. I think I can skip this. There are other ways people made foams. Here with this approach, you can see that you can get highly open cell foams. Then we can discuss if the porosity in the cross-section along the z-axis is homogeneous or not. This is one of the drawbacks of direct foaming, that often you might have some gradient porosity. But you can see with this approach that uses some oils like toluene and hexane in water, so you make an emulsion. You can obtain highly interconnected porosity. Okay, so I think we can skip this. So let me just summarize. We looked at different methods for the production of cellular ceramics. You can infiltrate and replicate a scaffold, a polymeric scaffold. Typically, you obtain foams with a porosity in that range, with certain cell size and and fully interconnected porosity. Then you have direct blowing, burnout sacrificial templates. These are some approaches that I will be discussing in a moment. And you can see that you can obtain wide ranges of features for your porous material by changing the manufacturing approach. Okay, this is simply another table that adds some information. One of the things that these are other alternative methods that that can be used. Of course, one possibility of obtaining poroceramic is partial sintering. In this case, it is not easy to obtain a large volume of porosity. And also you cannot control the pore size easily. Some people proposed an approach that has been used for making so-called microcellular plastics. So any styrofoam cup that you use for drinking, I guess they're not used anymore, but that was the cup was based on a process called that led to what is called a microcellular foam. And a microcellular foam has something like 1 billion cells per cubic centimeter. The cell size is really, really small. And the process was developed at MIT using supercritical CO2 that was mixed with the polymer. And then after extrusion serves simply the purpose of making a shape. The release of the CO2 because of the transformation from supercritical to gas would expand the material. And people in Korea have done that for using poroceramic polymers and filled poroceramic polymers, so they were able to produce different components with a cell size, an extremely small cell size. And if you remember, I mentioned that the cell size from the models is one feature that, as we will see when we talk about properties, that does not affect a lot the mechanical properties. But when you go for ceramics, when you have very small cell sizes, it means that you have also very small cell walls if the volume of porosity is high. And this leads to very high strength for the foam. Okay, it's partial sintering, we don't need to discuss. This is a very nice review paper where you will find a lot of information concerning different foaming methods and different characteristics for your ceramic, macroporous ceramics. And you can see that you can, depending on the type of fabrication approach, you can range in terms of pore sizes from 1 micron to more than 1 millimeter, and the porosity can range up to almost 90+%. So these are the typologies, the types of cellular ceramics that we can discuss. And again, this is the structure that they have. Extrusion is, of course, one very good way of obtaining specific types of highly porous ceramics. The advantage of this approach is that you have a high permeability. You also have high strength, perpendicular, parallel to the extrusion direction. The strength perpendicular to the extrusion direction is much lower. And you can see that people also have developed glass honeycombs. And the advantage here is that you can further process this glass honeycomb to make very specific components. So you have on one side large pores, and then you stretch the material, you retain the extruded pores, and you have a much smaller much smaller size. So this can be used, for instance, as ink reservoir and for high density array heads for combinatory chemistry and biological applications. Okay, so the connecting rods is what was obtained by direct inviting. I didn't mention that direct inviting was originally named robocasting. It was invented by Joe Cesarano at Sandia National Laboratories. He now has a company called Robocasting. And we don't need to discuss this more in detail because we already talked about that. So you can see some components produced in that way. Yeah, we don't need to discuss additive manufacturing. For connective, if you have a fiber mat, you can have a very large volume of porosity, and and you can form the mat by collecting the fibers that are randomly oriented in the length and width direction on a moving belt. And then you have issues in terms of the bonding strength if you lay up different fiber mats, but they can be stitched to provide rigidity also in the vertical direction. This is actually a piece of space shuttle tile. These are silica fibers, and the space shuttle tile was black because it was coated with a glass coating that would have high emissivity to cool down the material. This approach is really not interesting, but people have proposed to assemble hollow spheres that are produced using sacrificial templates typically. And once you do that, you can obtain porous ceramics. People have also realized that, as I mentioned, in nature, you have a lot of highly porous structures, and you can, of course, take inspiration from natural structures in order to come up with architectures that have enhanced functionalities. But people worked on making ceramic foams using a biotemplate. So they started using wood, for instance, infiltrating the wood with ceramic particles or ceramic precursors, and then burning out the wood to convert everything into ceramic material. In this way, you can obtain the benefits of the original wood structures. And you can see that by changing the type of wood, you change the characteristics of the of the porosity and therefore the properties of the material. So this was work carried out in Germany, and they actually interacted with experts in trees to select trees that would give you the most homogeneous and repeatable structure. But this type of approach is not really used anymore. Another possibility still developed in Germany was to use paper, and actually they manufacture paper using integrating ceramic particles together with the conventional cellulosic fibers. So they worked with a paper company to generate these ceramic filled paper, and then once you have your paper, you can make a lot of structures quite easily that you can then convert into a ceramic material. Once you have a macroporous component, for a lot of applications, this is not enough, because you would like to have additional features provided by your highly porous ceramic. And one of the possibilities is to generate high specific surface area in your porous ceramic, leading to hierarchical porosity. So in this case, depending on how you make your macroporous ceramic, you can have stochastic or non-stochastic structures. But the main point is to embed specific surface area. And a foam or highly porous ceramic, of course, has a lot of geometric surface area. And this is one of the reasons why people are interested in making these components. But the cell walls are dense, and this leads to a low value for the specific surface area. In order to have high square meters per cubic centimeter in your material, you need to have mesopores and especially micropores defined as pores with the size micropores below 2 nanometers. And the cellular ceramics are optimal substrates for generating hierarchical porosity because they have a large geometric surface. And the main point is that if you have a component with hierarchical porosity, you have higher, better improved properties over simply having a macroporous ceramic. For instance, you have a lower pressure drop with respect to a component made of a material that has only small pores, a higher rate of external transfer of mass, greater turbulence, increasing convective heat transfer. So there are two ways of developing high specific surface area. One is the assembling of micromesoporous materials into components that possess the micropores, or you add the micromesoporosity to the cellular monolith, for instance, by coating or by embedding particles into the raw materials. And you can have one-pot or multi-step processing routes. And because of the wide range of processing approaches available, you can obtain components with very varied morphology suitable for a variety of industrial applications. So without going into too much detail, you have you form your monolith with a hierarchical porosity, starting from micromesoporous components, and you can use hard colloidal templating. You can use biological templating. You can make emulsions, powder processing plus sintering. You can make microporous polymeric foam and impregnate and remake the template, or you can have phase separation. And here you can see some images of zeolite foam that was obtained by coating polyurethane foam and then followed by sintering. Of course, in this case, you have to be careful that when you sinter, you do not close the pores because the porosity in the zeolites is at the nanoscale. This is a range of approaches that has been followed, and you can see that the specific surface area values can go up to values higher than 1,000 square meters per gram. If you want to add micromesopores to microporous ceramic, these are different ways in which you can do it. So you can coat. One interesting feature of, for instance, polymer derived ceramics is that when you heat to high temperature, you can trigger the carbothermal reduction reactions, generating gases. If you have some metal catalysts in there, you can catalyze the in situ formation of nanotubes, or actually nanofibers, especially nanofibers. So you can grow on the inner surface of your porous material, you can grow nanofibers, and this, of course, increases the specific surface. So let me move to the last file. Okay, so let's talk about the properties of cellular ceramics. So we need to recognize that cellular solids significantly extend the range of properties of ceramic materials that are available to an engineer. So let me say it again. Cellular solids significantly extend the range of properties of ceramic materials that are available to an engineer, which means that if you add porosity to a solid, you obtain much different properties. You can see, for instance, of course, you reduce the density, you modify the thermoconductivity, you modify the Young's modulus, you modify the strength, and you shouldn't think of simply mechanical properties when you think of the properties of a porous ceramic, but also you should consider fluid transport, thermal insulation, and the maximization of surface area. So if you look at the work by Gibson and Ashby, who worked a lot on modeling of the properties of highly porous cellular materials, you can see that you can cover a very wide range of values in terms of density and compressive strength by changing the type of material you are working with. And ceramic materials are placed in this area. So ceramic foams allow you to obtain properties that cannot be delivered by other materials. And besides extending the properties of a solid, ceramic foams have a unique combination of properties, because at the same time, they have low density, they have low thermal conductivity, low dielectric constant, low thermal mass, and they, with respect to using fibers, for instance, a ceramic foam does not create a health hazard. At the same time, they have a high specific or geometric surface area, thermoshock resistant, and I don't need to read all of this, but you can see that you have a unique combination. And then you have a lot of parameters that you can play with that affect the properties, the relative density, so the amount of porosity that you embed, the cell morphology, so the macro structure, the size and distribution of the cell windows in the cell walls, and the density microporosity of the struts and cell walls. And you can further modify the surface or properties of cellular ceramics by providing wetting, absorbance, heterogeneous nucleation, bioactivity, sensing selectivity, catalytic efficiency. And here are some of the applications that can benefit from functional cellular ceramics. In terms of design flexibility, you can look at the pore size, the cell structure, and the characteristics of the porosity and the characteristics of the surface area. At the same time, you can modify the material, and this, of course, will change the strength, the temperature capabilities of the material, corrosion resistance, the conductivity, the density, and the coefficient of thermal expansion. And you can also think of augmented structures, integrated structures that have porous and non-porous components. You can have sandwich structures with phase sheets. You can add membranes to have micropores plus meso and micropores component for filtration. So one interesting feature of macroporous ceramics is that the properties can not only change with the porosity, but they change in a rather continuous way. So if we look, for instance, electrical resistivity, you have a strong decrease in the electrical resistivity with increasing porosity. If you increase porosity, you have, this is the decrease of porosity. So if you increase the porosity, go in this direction, you increase the permeability, you increase the corrosion rate, the mechanical properties decrease significantly with porosity, and as well the thermal conductivity. So the fact that you can combine different properties in this way means that you can actually use the porosity as a defining parameter for selecting the properties and optimize the combination of properties of your component. Because often in a component, you need to simultaneously optimize different features. So in terms of mechanical properties, of cellular ceramics. There are two main models for the interpretation of the mechanical properties. One was proposed by Gibson and Ashby. They have published a very, very nice paper called Cellular Solids, if I remember correctly. And the other one is the minimum solid area model. And the Gibson and Ashby model focused on the solid phase comprising the cellular structure, while the MSA model focuses on the gas phase. And the Gibson and Ashby model idealizes the cellular structure as composed of a number of hollow polyhedra, which are stacked and interconnected. And you can identify specific features in these polyhedra, the cell edges, the cell faces, and in the model, typically the polyhedra have the same size. And you can also quantify the balance between closed and open porosity using a parameter which expresses the fractional material present in the cell edges. So this is the model that has been used by Ashby, Gibson and Ashby to model the mechanical properties of a foam for any material, plastic, metal, and ceramic. And you can see that this is a bending dominated structure. So with load is applied, the strut breaks by bending. And this is the same structure with a closed cell. And by determining how much material you have in the cell edges, you can also take into account the presence of cell windows in the material. So if you have all the material in the cell edges, you have an open cell. If you and you can with this formula, you can take into account both open, closed cells, and also foams that have an intermediate distribution of the material within the solid, within the volume. And you can see that there is a certain dependence for the elastic modulus and the compressive strength on the as a function of density and therefore of porosity. There's one important thing to point out, that these are these values are parametrized based on the strength of the material. And for ceramic materials, you have issues in terms, you have issues in terms of determining the true strength of the material, because what people do, typically, they simply put into the formulas the bending strength of alumina obtained using a different approach. And the floor population of the samples is completely different from the type of floors that you generate when you do foaming, for instance, or when you process a highly porous material using a different approach. So sometimes this approach doesn't allow you to have proper modelization in terms of values for the behavior, but the trends are correct. I don't need to spend time to discuss the other approach. Simply, these formulas give you relations between mechanical properties, elastic modulus, flexural strength, compressive strength, and porosity. And in Gibson-Ashby model, the nice thing is that you can also take into account if the cells are open or closed, or if they are in an intermediate state. And you can see the typical results that you have from the minimum solid area fraction, minimum solid area approach. And you can see that depending on the porosity, you have different trends for your characteristics. when you have a foam and you subject it to tension or bending, you have that the crack nucleates a weak cell and or pre-existing flaw, and then you have catastrophic failure if you're working with a ceramic material. And you can see here, for instance, the data for a ceramic foam. In compression, things are different because you have the fact that the linear elasticity is controlled by the cell wall bending and cell face stretching for closed cells. So what happens is that you have a linear elastic portion of your of the behavior of your material, and then you have a collapse of the strength, but you do not reach zero, so you do not have catastrophic failure. You have a plateau region, and then when you start increasing the strain, the broken components touch each other, and then you start having the densification. So this type of behavior is very interesting, and you can see here what happens to the foam as a function of the deformation, the strain, and you can see that you do not have instantaneous collapse of the structure. And this is very, very useful for a wide range of applications. You can see here how the mechanical properties are affected by the relative density. So with decreasing porosity, increasing relative density, you increase the strength by orders of magnitude, and closed cells are more performing than open cells. These lines are the ones that come from the Gibson-Ashby model. These are the data for ceramic foams, and the fact that not all the materials fit very well. The curve depends on this fact that I mentioned, that it's difficult to quantify the real strength of the material that you need to input into the formulas. And the fact that not many closed cell foams are shown here is that a lot of people prefer to make open cell foams, so there are not many data available. So the fact that a foam breaks fractures in this way means that a foam can absorb more energy per unit volume at a certain stress than a solid. This is for a polymeric foam, but the same thing you can say for ceramic foams. So brittle foams are actually good for absorbing stresses, despite the fact that the maximum load they can sustain is limited to the presence of porosity. So, for instance, we worked on impact applications and specifically hypervelocity impact. So, if you have satellite that is in space, you have a lot of debris that can hit your satellite, and they typically, the speed for this debris is of the order of 10 kilometers per second. So this is called a hypervelocity impact. And people looked at the use of foams for absorbing the impact. And this is something that you can also relate to defense applications. We with the microcellular ceramic foams, we were able to stop a projectile traveling at 6 kilometers per second in a few millimeters of the foam because of the local crushing of the material absorbing the energy. For defense applications, for instance, people are interested in deflecting, absorbing the blast. If you have a tank, for instance, that goes over a mine, and the mine explodes, and nothing happens to the tank because of the protection of the metal sheets, but the people inside get a shock and they die because the brain doesn't like that type of shock. So we were tasked to investigate the use of cellular materials to deflect the blast. And if you use a metallic foam, which would be, let's say, a reasonable choice because of the strength and the possibility of plastic deformation and high energy absorption, it turns out that the foam compresses and changes its shape, and this leads actually to an enhancement of the shock wave. If you have a ceramic foam that crumbles, then you actually deflect reduce the shock wave. So this is one specific application where the high capability of cellular structures of absorbing energy can be exploited. Okay, so I don't need to, there are too many details, so I'm not going to discuss them. So for thermal properties, of course, you have different features. You have the gas conduction, the solid conduction, you have convection, and you have radiation. And for porous materials, and has been demonstrated that convection only plays a role when the cell size is large, and large means higher than 10 millimeters. And not typically ceramic cellular material has smaller features. So taking that into account, as a function of relative density, you have the change in conductivity of the gas. You have a change in conductivity due to the radiation component, and a linear change for the thermal conductivity based on the solid in the foam. And this leads to this overall behavior, which means that you can select for each material that you're interested in, you can select the best amount of porosity that would lead to the least thermal conductivity. In terms of thermal shock, you know that if you look at this equation, you can increase the delta in temperature at which you subject your material based on these parameters. This is the Poisson ratio. So one way of increasing the thermal shock resistance is to increase the strength of the material, or select the material with the best strength. Another approach for withstanding thermal shock is to decrease the coefficient of thermal expansion. So, of course, you go from alumina to, for instance, mullite, or you go to from zirconia to silicon carbide in terms of materials. But you also have this component, so the elastic modulus. So a good way of increasing the thermal shock of ceramics is to add porosity. This leads to a lower strength, but also to a lower elastic modulus. And the overall result is that you increase the thermal shock. That is why, for instance, in certain glazes, in certain ceramic coatings, you embed some porosity in order to improve the thermal shock behavior. One interesting point, which is should be rather obvious to people working on in material science. The coefficient of thermal expansion is not influenced by porosity. And this is, of course, due to the fact that it only depends on the type and strength of the chemical bonds that constitute the material. In terms of electrical properties, you have a decrease in electrical conductivity because of the tortuosity of the conductive paths that you generate in a highly porous material. So this is a good way, for instance, for producing components that can be heated using the Joule effect. And the dielectric constant is also reduced by foaming, and this allows, for instance, to generate structures for transmitting microwaves. People have been interested in developing electrically conductive foams, and you can see here some examples. And the idea is that you can provide additional features to your component in this way. And that was a silicon carbide, the one on the right, Ligafil. It was developed by IKTS in Germany, Fraunhofer Institute, and they have used this for catalytic reactions. Okay, I can skip this. You can add magnetic fillers, and then you obtain magnetic foams. And you can see that if you embed, for instance, iron silicide powders, then you can have magnetic behavior in your material. The last property I will be discussing is permeability. And you can describe the permeability using Darcy's law, which is valid for low flow rates. And you have a parameter K1, which is related to the viscous attrition within the material. This is the length of the material. This is the pressure drop. And this is the viscosity. And Ni is the velocity. And for higher flow rates, you have non-Darcian permeability. And you can come up with different formulas, and the Darcian correlation considers only viscous effects, while the non-Darcian correlation is more general and takes into account inertial and turbulence effects. You can also use Ergun's equation to relate the K1 and K2 parameters to the characteristics of the porous medium, for instance, the porosity and the mean pore dimension. So without going into too many details, we can say that permeability in cellular material is ruled mainly by the cell size. And if the cell size is constant, the permeability, of course, depends on the amount of porosity in the body. And when you talk about cellular ceramics, in particular foams, or cellular materials, in particular foams, people often talk about pore per inch as a way of describing the size or the porosity of the material. I just wanted to show, okay, this. So there is a researcher in Brazil who is an expert in permeability of cellular materials, not just ceramics. And he compiled a large set of experimental data coming from a wide range of researchers. And you can see that the Darcian constant and the non-Darcian constant are interrelated. And the interesting thing about this approach is that you can see that if you have low permeability materials, then they sit in this range of values. Here you have materials that are fibers or granular filters or foams obtained, for instance, by gel casting. So they have a structure where you also, that is of course permeable, but you also have cell walls. And with increasing, not with increasing porosity, but with modifying the morphology of the pores, for instance, using highly interconnected pores and or honeycombs with direct channels, then you can have very high permeability. So I think that I can show you quickly some applications for ceramic foams or cellular ceramics. If you have open cells, then metal, molten metal filters or exhaust gas filters can be obtained. Heating elements, porous electrodes, porous burners, aeration of liquids, bone replacement, cell enzyme carriers or release, catalyst support. And one interesting feature that I didn't mention, one interesting possibility is that if you have a cellular ceramic, you can infiltrate it with metals, or you can infiltrate it with polymers. And what the ceramic does is that, of course, it provides characteristics to the bulk material that the material itself wouldn't have. So, for instance, we infiltrated ceramic foams with polymer, and then we created some components for bullet-proof applications. If you add if you infiltrate with a metal, you can generate a very strong interface between the metal and the ceramic, which is positive. The ceramic typically has a high elastic modulus, certainly high hardness. One of the things that we found out, so we did that with the idea of increasing the hardness of the metal. But what we found is that when you do a wear test, what happens is that the ceramic foam fractures, and if you quantify the wear by the weight loss, then you have chunks of material that are released, and the wear resistance appears to be lower. But there are other people that have demonstrated that you can make components with very interesting properties if you combine metals with cellular ceramics. If you have closed cells, this is a wide range of possibilities for applications. High temperature sound attenuation is also a very important topic. And if you have specific types of ceramics, you can modify, you can have, with anisotropic cells and graded porosity, you can obtain a wide range of components. So I think that we can stop here.
Sir, want to hear some insights about that porous ceramics for blast related, which you mentioned. Whether it is dense ceramic of porous with a porous metallic structure sandwich, or ceramic itself should be in.
So for that application, it was simply porous ceramic. Of course, it was a sandwich structure with a metal face with a ceramic inside, the porous ceramic inside.
Okay. So if I would like to have some insights, if some references is there, we'd like to see, sir.
So this work was carried out with a company and the defense ministry in Italy, and the results cannot be disclosed. But the results were positive. So they blasted 3 tanks where they were mannequin, that was instrumented, and they verified that the amount of stress that the person was subjected to was lower.
Good to know. Porous ceramics and glass.
Yes. I published something on hypervelocity impact. So if you send me an email, I can send you a copy of the paper.